Hey guys, this is for Friday. This YouTube. I'm going to try to stick to about 25 minutes. I'm going to try to stick for about 25 minutes. Just a reminder, you have a quiz. You have a quiz this Friday. It's during class time. It's just going to be on Canvas, loaded on Canvas. It's there. It's in your files on Canvas. It opens at 9 o'clock for my 9:05 class, and opens at 10 o'clock for my 10:10 class. And you have an hour to do it and submit it. It should only take 20 minutes. Again, we have a test 3 next Friday. I've decided it's only going to be on the content that we've covered in Chapter 4 and Chapter 5. Okay, so that will be. Right now I am not anticipating it will be like the last test. Okay, we may have a small WebAssign part, but it will only be like 25% of the test, not 68% of the test, and then the rest of it will be more similar to what we had on our test 1. Okay, so it'd be more handwritten work. It will be timed, just like last time, but we'll talk more about that next week. Okay, so what I want to make sure now is that in this short lecture, you have enough information so that you can at least do the homework in section 6.3, which is our introduction to integration. Okay, we start off by just trying to see what this Riemann sum stuff is, and we've got to work through it a little bit before we hit the magic result that changed mankind, which is the fundamental theorem of calculus. Okay, and that's section 6.4, which is your reading. Now the homework that I assigned is in the book, okay, but it's actually on the PDF. It's actually on the PDF because a lot of the stuff they have in the book is just busy work, okay, and I didn't want you guys having to do a lot of busy work. But now just a reminder of, I think that got the nuts and the bolts. I miss you guys. I so wish we were in class. I so miss having you guys in my class and being able to stand on desks and get you guys up and moving. But this isn't forever. This isn't forever. This is for weeks. Okay, so let's go back to where we were. Okay, remember the definite integral looks like this symbol, and it just represents a number. It just represents a number. It's a complicated number, I agree, because it's defined in terms of a limit where n is this like partition of our closed interval a, b, and I know it doesn't make any sense right now. You're just hearing words. Okay, we're taking the limit as n goes to infinity. Remember, calculus is about limits, derivatives, and integrals. Derivatives and integrals are defined in terms of limits. Then we've got this sum that goes from 1 to n, and then we've got our function that we're sticking x sub k values into, and we're multiplying each one of them times delta x. So this is a k, where our delta x is this little partition length. It's b minus a over n. So for each one of these n's, we're chopping the closed interval a to b into that many pieces, and these x sub k's that we're plugging into our function start at a and then move over at delta x until we reach the other side of the interval. And the way that we do this is we say x sub k is equal to a plus k times delta x, where k goes from 0 to n. Now the problem is that the limit is n goes to infinity, and so for centuries, millenniums, all we could do is get approximations until Leibniz and Newton came along. And well, I'm going to remind you that calculus didn't really come around until 1700. Okay, so William and Mary was created. William and Mary was founded before calculus. That's how kind of new calculus is. You know, like Dr. Warren, that's 300 years. I know, that's a long time, but not in grandma lives, okay? If you go back a certain number of grandmas, what the hell are you talking about, Dr. Warren? If you go back a certain number of grandmas, I mean, a lifetime's that, yeah, I'm almost 60. I mean, it's gone by really quick. Those 60 years, okay? So it's not really that long, okay, ago, as far as when calculus was here. Okay, so now let's try to unpackage this. What we've got is we've got a function. So we'll just draw that. So I think everybody, if I draw, you draw. If I draw, you draw. Okay, we got a function and we got an interval a to b. So we started doing this last time. Okay, now we can't really, I know you guys struggle with that notation. I know you struggle with it. So I'm just going to look at it in its written out form. This just means f of x1, we start at 1 times delta x, plus f of x2 times delta x, and then we just go all the way over till we stop at n, f of xn times delta x. Okay, now let's just take a simple example where n is not infinity. Where n is not infinity. Let's make it simple like we were last time. Let's just say n is equal to 4. Let's just say n is equal to 4. Then we've got f of x1 times delta x plus f of x2 times delta x. We keep going until we reach 4. F of x3 times delta x plus f of x4 times delta x. Okay, so if you wanted an approximation, a horrible approximation, but an approximation nonetheless, if you just chose n equals 4 and calculated this, that would be an approximation to the integral. And like that one, I'm still not getting it, because who is this delta x? And who is x1, who's x2, who's x3, and who's x4? Okay, and that's what we're going to try to unpackage in this interval today. Delta x is b minus a over n. So in this case, it would just be minus bb minus a over 4. Now down here in our picture, it would be like here's b, here's a. If we do b minus a, it's this distance from here to here. Again, Dr. Warren, say that again. If we look at the numerator, b minus a, it's just the distance between b and a. Now what we're doing is we're cutting that distance into 4 pieces. So 4 is nice for me because I just need to cut in half and cut in half again. So we're taking the interval and we're cutting it into 4 pieces. Okay, now the distance of each one of these pieces is delta x. You're like, okay, Dr. Warren, I think I could get that. If you gave me a function and you gave me an interval, I think I could divide it by 4, or whatever the n they gave me. I think I could get an approximation, at least for the delta x. But who is this x1? Who's this x2? Who's this x3? And who's this x4? Well, we've got to use this. We've got to use this identity to find those. And again, it's not near as hard as it seems when you look at when you first see the definition. I know everybody was like, I'll never understand this. I'm never going to understand this. But it's not as hard once you just start unpacking it. If we look here, we have this x sub k is equal to a plus k times delta x. Now we notice the first k that we use is 0. So wherever I see the k, I put a 0. But 0 times any real number is 0. Or we just get that x0 is a. So this is x0. Now x1 is equal to a. Now k is 1, because we're going all the way up to n, plus 1 times delta x, which is just equal to a plus delta x. So we add a delta x over from a, and we get x1. And x2 is just equal to a plus 2 delta x's. So we just go over another delta x, and we get x2. Now, like, Dr. Warren, this isn't so bad. and we go over another one. K is now 3, and we get x3. And then when we go over to n, we get our last one. In this case, it's, I know I'm not talking to you. In this case, it's 4. And we get x4. You're like, okay, Dr. Warren, that's not so bad. I think I can find delta x. They give me the b, they give me the a. I cut it into how many pieces they tell me. 4, 6, 8. I'm not doing 100. I'm not doing 100. And then I find the x sub k's. And then what you do is you plug them into the function. You plug them into the function, okay? So like, for example, to get f of x1, I'm going to plug it into the function. Now let's just come on up and go play the game that we played before. We go up, we go over. So we plug it into the function, we get f of x1. We plug it into the function, we get f of x1. Okay? And then once we have that numerical value, we just find what f of x1 is, and we multiply times delta x. And then we plug x2 in. So maybe that's f of x2. And then we add on f of x2 times delta x. And then we do the same thing. We find x3, plug it into the function, come over. Here's f of x3. And we multiply that times delta x. And then we do the last one. And we plug that into the function, and here's f of x4. We plug that into the function and multiply times delta x, and there's our approximation to the definite integral. There's our approximation to the definite integral. And you're like, Dr. Warren, who gives a crap? What is this about? Well, graphically, well, I want to do a problem like I assigned. I'm just going to make one up. Just to make sure you know how to do this. But I wanted to talk about where we're heading. If we look at this, f of x1 times delta x. Here was my f of x1. Here's my delta x. Now if I look at the area of this rectangle, how do you find the area of a rectangle again? Suppose you've got something that's like 2 feet by 7 feet. How much carpet would you need? How much carpet would you need to fill that rug area? If it's 2 feet this way and 7 feet that way, how many square feet do you need? You're like, Dr. Warren, you just multiply length times width, so it'd be 14. That's what you would need. 14. This was 2 feet, that was 7 feet. You need 14 feet squared. How do you find the area of a rectangle? Well, if you look at this, this is a rectangle. Its width is delta x. Its height or length is f of x1. So this distance here is the same thing. This side distance of this rectangle is the same thing as f of x1. So then the area of this rectangle is f of x1 times delta x. Similarly, if you look at this one and you look at this rectangle, its width is also delta x. So the area of this rectangle would be f of x2 times delta x. Now what would the area of that rectangle be? What would the area of that rectangle be? And I hope you're like, well, Dr. Warren, that would be f of x3 times delta x. And then this would be f of x4 times delta x. And so what we see is that when we add up these 4 little rectangular areas, we get an approximation to the area of this bizarre looking shape That's the area under the function down to the x-axis between a and b. We get an approximation to that area. Now the larger we let n get, the more subintervals we get, the better that area approximation gets. But that's not what tonight's homework's about. That's not what tonight's homework about. Tonight I'm just having you actually calculate some of these Riemann sums. So that's what I want to do now. I want to look at a specific example, and then I'm just going to, because you have a quiz, I'm going to stop, okay? But this, I want to get you enough where you could actually calculate some of these things. So let's talk about a function. Maybe we got f of x equals x squared plus 3, and maybe we're looking at an a and a b going between, let's just say, 1 and 8, and I want you guys to approximate that definite integral. I want you to approximate, let's make it 1 and 9, so it'll be, approximate that definite integral within, using a Riemann sum, specifically a right-handed sum. If you had done your reading, with n equals 4 subintervals. Okay, so if I was doing that, I would like to calculate this approximation right here. I'm not even going to ask you to graph it. We could graph it, and we'll look at that. We'll look at that in Monday's lecture. But the first thing you got to do is identify who's A and who's B. Okay, I'm looking at the clock, and I'm a little worried about my timing. This would be A. This would be B. Now what you're trying to do is calculate this. I'll get out of the way. I'm just rewriting what I had over there. So the first thing I need to do is calculate my delta x. So it's b minus a over n. Now who's the b? Who's the b? And you're like, Dr. Warren, I got that. That's 9. That's the 9. Who's the a? 1. And who's the n? And you're like, Dr. Warren, you just put a box around it. That's 4. So my delta x would be equal to 8 minus 4, which is 2. You're like, Dr. Warren, this is the first thing in my class, this class I've actually understood. Okay, 8 minus 4 is 2. So there's delta x. The next thing I need, I don't know what happened to my voice. The next thing I need is my x1, my x2, my x3, and my x4. So I just come back and I look at the formula, x sub k equals a plus k times delta x. So I have x sub k equals a, but my a is now 1, plus k times delta x. Maybe I'll do this where I put it in like this. A plus k times delta x. But who's your a now? And you're like, well, Dr. Warren, that's 1 plus k times delta x, but your delta x is 2. So x0 would be equal to 1 plus 0 times 2, which is just 1. x1 is equal to 1 plus 1 times 2, which is 3. x2 is 1 plus 2 times 2, which is 5. x3 is 1 plus 3 times 2, which is 7. And x4 is 1 plus 4 times 2, which is 9. Okay, Dr. Warren, that doesn't seem so bad. Well, now let's find these values. F of x1 well, f of x1 you just found was 3. So it's going to be f of 3. It's going to be f of 3. You're like, well, how do I find f of 3? Well, here's your function. So wherever you see an x, you're going to put a 3. So this would be equal to 3 squared plus 3, which is 12. Similarly, f of x2, this guy, f of x2, we found x2 to be 5 using my function 5 squared plus 3, which is 28. F of x3 is f of 7, which is 7 squared plus 3, which is 52. You better check me. F of x4 is, that's a 4, is f of 9, which is 9 squared, which is 81 plus 3, which is 84. You're like, Dr. Warren, are we done? We're close. We're close to being done, guys. We're close. Now I need to get this approximation. So it's f of x1 times delta x. So I'm writing this down again just because you'll have it in your notes. Okay, now f of x1 we found was 12. My delta x we found to be 2. F of x2 we found to be 28. Delta x is 2. I'll just be quiet. I don't know why we need sound effects. Okay, there. And f of x4 we found there. And now it's just a matter of grabbing a calculator. Now it's just a matter of grabbing a calculator and calculating 24 plus 56 plus 104 plus 168. You add all those together, and that would be our approximation. That would be our approximation here to our definite integral. You know, like, Dr. Warren, that's a lot of work. No, I get it. It is a lot of work. It's a ton of work. Okay? And that's just for n equals 4 subintervals. And we're letting n go to where? We're letting n go to where? Infinity? Dr. Warren, we're not going to calculate a single one of these. We're not going to be able to do a single one of them. Well, fortunately, Newton gave us a clever way of being able to bypass having to do that infinite limit, okay? And that's called the fundamental theorem of calculus, and that's where we're heading. I want you to read about that in section 5.4, but tonight I want you actually calculating these. Now, I didn't pick a lot of subintervals. Your book picked things like 10. I'm not making them do 10. I'm not making them do 10, okay? And one point I think they said 12. I'm like, seriously? That's a lot of busy work. I think I picked 2. N equals 2 and even n equals 4. So it's not bad. Now again, if you're doing this Riemann sum approximation, you got to know who your A and B is, step 1. Divide that B minus A into whatever n is, get that value, start at A, and keep adding delta x. So we started at 1, add 2, that's the next one, add 2, add 2, add 2, until you reach B. Plug these values, x1, into your function, not so bad here. Get those numerical values, multiply them times delta x, and there's your Riemann sum. So I think I assigned maybe like 4 or 5 problems with 2 different ends. What you're going to want to do is go through those, work through those for Monday, okay? But that's it for today. That's it for today. Like I said, I promised you a shorter lecture today, okay? Just setting you up, okay? And on Monday, we're going to start the theorem that changed mankind. We're going to start the theorem that changed mankind, which is the fundamental theorem of calculus. Okay, I hope everybody has a wonderful weekend. I hope everybody's families are safe, and can't wait to see you guys again. All right, bye-bye.